Hey guys, this is lecture 33. Got a quote here from Elder Runland that I'll read for you. Our Heavenly Father's goal in parenting is not to have his children do what is right, but is to have his children choose to do what is right and ultimately become like him. I like that. So during the quarantine or during the coronavirus stuff, choose to do what's right and stay home as much as possible. Keep everyone else safe as much as you can. Today we're going to be talking about heat capacity and heating curves. And this really just has to do with how quickly things heat up when you add heat to them, or how their temperature changes as you add heat to them. So to give you an example of what we're talking about, in a room, let's say you're in a room that's about 72 degrees Fahrenheit. Everything in that room equilibrates to that temperature. So including the chair, the desk, the carpet, the bed, everything's going to be at the same temperature. So why do some things, like let's say this chair is made out of wood or metal, why is that going to feel colder than sitting in, let's say, a chair right here made out of fabric? Well, in all of these cases, heat is flowing from a hotter to a colder object. If the room is at 72 degrees Fahrenheit, then you are the warmer object. Skin temperature is usually around 91 degrees Fahrenheit. So if everything's 72 degrees Fahrenheit, the heat is always flowing from you to everything else. But metal feels colder because it conducts heat much more efficiently than fabric. So metals are good conductors of heat, and any difference in temperature feels like it's cold or hot. So for example, if you have some bleachers out in the sun or in the snow, or if you live in Arizona, like I did in high school, anytime you touch your seatbelt in summer, you've just burned your hand, or if you sit on it with shorts, you just burned your leg. But in these cases, any difference here is going to be really noticeable. And then of course things can just be, things can also be at just different temperatures when you give them the same amount of heat. So for example, let's say it's the middle of the summer and we can do this. Well, we can't do it in Phoenix because in the middle of the summer, the grass is pretty scratchy in Phoenix. So let's go to Central Valley, California. The blacktop, super hot, you burn your feet on it, but walking on the grass still feels comfortable. Why is that? Well, they've both been in the sun all day. They've both been getting the same amount of heat, but if you measure the temperature of the asphalt and the grass throughout the course of the day, so on the bottom here, I have the number of hours that have passed during the day, and then on the Y, we have the temperature. You'll notice that at different times, the asphalt is significantly hotter than the grass. Why is that? Well, they've both been sitting in the sun, but they have different heat capacities, which means it takes a different amount of energy to get the grass hot than it does to get the asphalt hot. So a heat capacity, what we're talking about specifically, is the amount of energy needed to raise the temperature of an object 1 degrees Celsius. And so different heat capacities result as a function of different molecular structures and different intermolecular interactions. So the more interactions things have, the more places to put heat, the more it can dissipate. All right, so this equation I'm going to move right up here to the top of the screen. This is what we call our heat capacity equation. And this is the equation for the heat capacity of a specific object. So let's say that you have a hard drive in your computer. You need to know its heat capacity so that you can know how much energy you can put into your hard drive before it overheats and melts. And then you're going to use that information to figure out how much cooling you need in your system, how powerful of a fan, how much ventilation, etc. So for this equation, this is the heat capacity of a specific object. In chemistry, though, we don't usually deal with objects. We usually deal with moles of things. And so this is the molar heat capacity equation. So you'll notice that in the usual heat capacity equation, we have a capital C Down here we have a lowercase c, and we threw in an n to signify the number of moles. So in this sense, the heat capacity is the quantity of energy required to raise the temperature of 1 mole of a substance by 1 degree Celsius. You'll notice there's a difference in units here too. In this heat capacity, the units is joules per degree Celsius, whereas here, this heat capacity is in terms of joules per moles times degrees Celsius. All right, we can also do this in grams, which is also very common. When we measure our heat capacity in grams, or grams times degrees Celsius instead of moles times degrees Celsius, this is what we call the specific heat capacity. All right, so when we're talking about heat capacity, that's the heat capacity of an object. Molar heat capacity is the heat capacity of 1 mole. Specific heat is the heat capacity for 1 gram of a substance. Why they called it specific is the same reason that we call monkeys monkeys, is because somebody called them a monkey, and that's what we've been calling them ever since. Now, the specific heat capacity of water is 1 calorie per gram degrees Celsius. Make sure when you're looking at these things that you always pay attention to the units. So notice this is the specific heat capacity, right? And it's 1 calorie per gram times degrees Celsius. This is not the molar heat capacity of water. Okay, now there's a few things like this, 1 calorie per gram degrees Celsius, that you should just know. So on this slide, I'm going to just go over things that you need to memorize. So just memorize these facts. On the exams, we're just going to assume that you know them. And again, remember that this material is not covered on exam 3. It's just covered on exam 4. So maybe you want to push back memorizing these until after exam 3. And maybe review this slide right before you take the next exam. All right, but the specific heat of liquid water is 1 calorie per gram times degrees Celsius. And that is equal to 4.184 joules per gram degrees Celsius. 1 calorie is the heat required to raise the temperature of 1 gram of water by 1 degree Celsius. This is the same thing that I said in this sentence, just reworded. Now this next one we went over last time, but 1 capital case calorie is equal to 1,000 lowercase calories, or 1 kilo lowercase calories. You know, the SI unit that we use for energy is joules, but in America, on our food products, and in a lot of other places in the world, we use calories. So you should just memorize this conversion between calories and joules. I believe it is on your equation sheet, but it'll save you a lot of time if you just memorize it. So 1 calorie, lowercase calorie, is equal to 4.184 joules of energy, and this is an exact ratio. So it's exactly this much. Now this part, 1 joule being equal to 1 kilogram times meter squared per second squared, you don't necessarily need to memorize that one. I usually have to look it up when I use it, but if you do memorize it, it will save you some time mathematically. Problem is, if you remember this one wrong, it's going to cost you a lot of time. All right, something else you should remember is the density of liquid water is 1 gram per cubic centimeter. Of course, a cubic centimeter is equal to 1 milliliter. And so the density of water is 1.00 grams per milliliter. Make sure you remember that. And of course, you should know that atmospheric pressure at sea level is 1 atmosphere. Okay, so learn this slide backwards and forwards. Now let's go back to heat capacities of other things really fast. So what I have here is just a chart where I have elements here, the heat capacities of these guys. So here I have their specific heat capacities. Here I have their molar heat capacities. So up here I mostly have metals, except for I also have graphite. So I have carbon in the form of graphite. And then down here I have some other species. So what you'll notice is up here in these metals, these all have heat capacities of less than 1, and species like gold and lead here have heat capacities of about 0.1. Now we compare these to the heat capacity of water, which is 4.18. You'll notice that metals have significantly lower heat capacities. Okay. So let me ask you a quick eye clicker question about this. The same quantity of thermal energy is added to equal masses of 4 metals: aluminum, copper, iron, and titanium. I have all their heat capacities listed here. You'll notice these are in joules per grams times degrees Celsius. But all of these metals are initially at the same temperature. Which metal has the highest final temperature if we add equal amounts of energy to each of these? So let's say we take each of these and put them in the sun for a little bit. Which one is going to heat up the fastest? Which will have the highest final temperature? If you want to pause that and think about it, you can. But the way we're going to think about this is the higher the heat capacity, so aluminum has the highest heat capacity of all of these. The highest heat capacity means we have to put in more energy to raise the temperature. So aluminum is going to increase in temperature the slowest, whereas copper right here, which has the lowest heat capacity of these highlighted guys, it's going to take the least amount of heat to raise this guy in temperature. And so copper is going to have the highest end temperature. Now, we'll get into this question of how we measure heat capacities next time. Right? But now I want to draw your attention to water right down here. And you'll notice on this chart first that we have water at -10 degrees Celsius, water at 25 degrees Celsius, and water at 102 degrees Celsius. So this top one is ice, this middle one is liquid water, and this bottom one is gaseous water. And you'll notice that water, liquid water, has a heat capacity of 4.18, ice has a heat capacity of 2.11, and gaseous water has a heat capacity of 1.89. So the heat capacity doesn't just depend on which species you're talking about, it also depends what phase you're in. All right, but let's talk about water for a second. It has this high heat capacity of 4.18, and because water has a high heat capacity, it's able to absorb large amounts of energy without changing temperature very much. This is why oceans and pools don't change temperature very rapidly. This is why in Phoenix, your pool is still usually refreshing halfway through the summer. And usually past July, August, your pool starts getting super warm, and then you have to do other stuff to cool it down. This also explains why in deserts, you have high swings in temperature from day to night. So it's really hot in the day when the sun's beating down on you, but really cold at night. The reason is because there's no humidity in the air, and that humidity, since there's no humidity, the atmosphere has no way of moderating its temperature, and so it's just depending on how much sunlight comes in and how much is being radiated off by the sun. This is why if you're in a really humid place like Hawaii, going into the shade doesn't help you cool off nearly as much as, say, in a desert, because in Hawaii there's so much humidity that the air just transmits or just carries tons of heat to you that will just keep dumping on you. And it's why the human body can be kept at a near constant temperature. So the high heat capacity of water means it can store large amounts of water. But why is the heat capacity of water so large? Well, it's mostly because it has hydrogen bonds everywhere, right? These hydrogen bonds are high in energy. And so when you put heat into water, a lot of that energy goes into the hydrogen bonding, either disrupting them or rearranging them. And so water has a really high heat capacity. Now water has 2 hydrogen bonds. Ammonia, which is NH3, has 3 hydrogen bonds. So you'll notice ammonia has a slightly higher heat capacity than liquid water, even at the same temperature, because it has more intermolecular interactions. So more interactions means more heat capacity. That also means that you have more ways of disposing that energy. That gives you a higher heat capacity, right? So let's practice now talking about how we're going to deal with this mathematically, because a lot of these problems you're going to face are going to be math questions. Let's say we're at an elevation where the boiling point of water is 93 degrees Celsius. We have 1.33 kilograms of water at 30 degrees Celsius. And that absorbs 290.0 kilojoules of energy from a mountain climber stove before the stove runs out of fuel. So we've poured water into a container on a stove and we're trying to boil it. What is the amount of thermal energy, or was the amount of thermal energy sufficient to heat the water to its boiling point? Well, we're going to have to calculate how much heat was used, or how much heat is needed to get to our boiling point, and we're going to be using our specific heat equation here. We know we're going to be using our specific heat equation because our amount was given to us in grams rather than moles. So when you know our mass, our heat capacity of water, you should have memorized by now. It's 4.182. Then for our change in temperature, the way we're going to calculate that, it's going to be our final temperature minus our initial temperature. So in this case, our mass is 1.33 kilograms. We're going to have to change that into grams. So we get 1,330 grams. Our heat capacity is going to be 4.184 joules per gram times degrees Celsius. Dang, I said it was 4.182. I got it wrong. Dr. Mortensen gets an F. And our change in temperature then, our final temperature, we're trying to boil it up to 93 degrees Celsius. We're starting at 30 degrees Celsius, so it's going to be 93 minus 30. So our delta T will be 63 degrees Celsius. Then we just plug these 3 values into our equation here. We'll notice that grams cancel out grams, degrees Celsius cancels out degrees Celsius, and we'll be left with a value in joules. Usually these joules will be really big, and so we will change them into kilojoules. So it takes 350 kilojoules to boil 1.33 kilograms of water, but we only put in 290 kilojoules before we ran out of fuel. So that was not enough heat to boil our water, and now the hiker has dysentery. Let's try it this way now. This is a different way of approaching this same problem, but at an elevation where the boiling point of water is 93 degrees Celsius, we still have 1.33 kilograms of water. We're starting at 30 degrees Celsius, and we're going to give it 290 kilojoules of energy from the mountain climber stove before we run out of fuel. Let's figure out what the final temperature of the water is. So we're still starting with our specific heat equation here, but now I'm asking you to solve for the final temperature. Go ahead and pause the video now and try and figure that out. Okay, so what we have to do now is solve for the final temperature. So we're going to have to divide by the mass and specific heat. So we're going to have to add the initial temperature to both sides. So we're going to have our final temperature equal to our heat divided by our mass times specific heat capacity plus our initial temperature. Our math will end up looking like this. When we run all those numbers through our calculator, we'll find that our final temperature is about 82 degrees Celsius. Okay, so that is the math, but it actually gets a little bit more complicated than that. And the reason is because of phase transitions. So I'm going to start this off with a question that's actually really important for the way you're going to work these problems. The question is, can liquid water ever get hotter than its boiling point? The answer is a very strict no. No, no, no. Water can never be hotter than its boiling point. We can change the boiling point. We can change the boiling point by changing the pressure, or we can actually change it by adding salt, right? So we've talked about those things, but every solution of water has a specific boiling point, and the water cannot get hotter than that point. So you can change the boiling point, but once you're boiling water, if you stick a thermometer in there, let's say this is 100% pure water, and the boiling point is 100 degrees Celsius. Well, if you stick your thermometer in there, that thermometer will keep reading 100 degrees Celsius no matter how much heat you put into this system from your stove, right? So your stove is still there, still adding energy, bubbles are boiling out, but where is all the energy going? The energy is going into breaking the intermolecular interactions between water molecules. So here I have a zoomed in picture. Well, it's a model, not really a zoomed in picture, but we have ice. You remember ice forms these hexagonal structures, but when we heat that up and add the heat of fusion, which is the energy required to disrupt all these bonds, then all these bonds are broken and water can jump around all jumbly mumbly. So the heat of fusion is the energy required to break these intermolecular interactions. So the way we calculate, or the way we do the math with our heat of fusion is we use this equation, where our heat is equal to our number of moles times the delta H of fusion. So our delta H of fusion is almost always listed in moles, but our specific heat capacities are usually given, which are in grams. So that's just something chemists do to you just to make your lives a little funner. All right, but let's talk about this a little more. The enthalpy of fusion, right? That's the amount of heat you have to put into ice to convert it into liquid water. But that is the amount of energy you have to put in to overcome the intermolecular interactions of the solid. And then for going from a liquid to a vapor, that's your delta H of vaporization. And that's the amount of energy that you have to you put in to overcome the intermolecular interactions of the liquid. Yeah, I feel like I'm stumbling over my words so bad today. I feel so much more nervous making these videos than I do just lecturing you guys in person. I have no idea why. I just feel it's probably because I keep watching it and hearing my own voice, realizing how much I hate it. All right, but don't hate yourselves. No negative self-talk. Dr. Mortensen, your voice is lovely. All right, sorry. But this is why our processes of going from ice to liquid and from liquid to water are endothermic, because you're having to put energy into the system to break these interactions. This is why when you recreate these interactions, you get exothermic processes, because when these guys are sticking together, now you have all that extra energy that was wiggling about, it just gets put off in the form of heat. Well, this is something we went over last time, so I'll just skip over it. All right, so now let's say you're hiking, but you're hiking in a really cold spot. So instead of starting with really warm water at 30 degrees Celsius, you're starting with snow, okay? So you're camping in the winter and want to make 1 cup of hot cocoa using 250 grams of clean snow. You're a weirdo that brought a scale and measured out exactly 250 grams and stuck your thermometer in the ice to find that it was negative 20 degrees Celsius. All right, so the clean snow is your water source. How much heat do you need if you want the water to be 98 degrees Celsius when you stir in your cocoa? Okay, this is where it gets complicated. Let me start by pulling up this plot here. What I have on this plot on the x-axis is the heat we're adding to the system, and on the y-axis I have your temperature in degrees Celsius. You'll notice several things. You'll notice a curve or a line down here labeled solid only. So in this region, we're starting at negative 20 degrees Celsius, and as we add heat, we're increasing the temperature of our ice until we get to our melting point. Then we go through a phase transition where while we're putting in heat, we're not increasing the temperature, but we are breaking intermolecular interactions. Now we're, now we're a liquid. Now we're heating up the water, and that's going to keep heating up until we hit 100 degrees Celsius, which is our boiling point. Then we're going to undergo a phase transition where we're again adding a bunch of heat, not changing the temperature. And then we finally get enough temperature to where or enough heat where it's all gas, and then it starts heating up the gas. Yeah. Okay, now each of these regions has its own different equation for calculating heat. So this solid only area, we'd use our specific heat for the solid. So our heat is equal to the mass of the solid times the heat capacity of the solid times our change in temperature. Then we have our solid liquid phase transition. So the heat there is going to be our number of moles times our delta H of fusion. We're going to have a heat equation for the liquid region. That's going to be our heat equal to the mass times our specific heat of the liquid times our change in temperature. And then here as a gas, or going from a liquid to a gas, and phase transition is going to have a heat equation where heat is equal to the number of moles times our delta H of vaporization. And then of course we have one more equation for the gas, where this is the mass times the specific heat of the gas times our change in temperature. Now we're not dealing with this whole plot. We're going from negative 20 degrees up to 98 degrees, which is slightly below our heat capacity. So the way we're going to figure out how much heat to go from here to here is we're going to add all three of these lower equations together. Right? So our heat's going to be equal to the heat required to heat the ice plus the energy required to melt the ice plus the heat required to heat the water. Okay, let me throw some values up here real fast. So the heat, or the specific heat of the ice is 2.11 joules per gram times degree Celsius. Our delta H of fusion is 6.01 kilojoules per mole. And our specific heat for the water is 4.184 joules per grams times degrees Celsius. Okay, now this is something that will trip you up once or twice. Let's start by just heating up the ice. How much do we need to heat the ice to get it to 0 degrees Celsius? So we're using this equation, right? We got our mass times our specific heat times our delta T. Our mass is 250 grams. That's just given to us in the question. We have our specific heat of the ice. And now this is the part that trips people up. For the ice, we're only going from our initial temperature of negative 20 degrees to our final temperature of the ice. So it stops being ice at 0 degrees Celsius. So we're not going to go all the way from negative 20 degrees to 98 degrees. We're just going to go from negative 20 degrees to our phase transition. So our delta T here will be 0 minus negative 20. That's of course 0 plus 20. So our change in temperature will just be 20 degrees. And then we'll plug in all the math here and find out how many joules of energy that takes. Then after we've heated it to 0 degrees Celsius, now it's going to undergo our phase transition. So we'll have to figure out how many moles of water or ice we have here. So we'll take the 250 grams and divide it by the molecular weight of water here and times that by the delta H of fusion. And then when we can work all that math out, find out how much energy it takes to go from a solid to a liquid. Now we have liquid water. That's at 0 degrees Celsius. And now we need to add heat to bring it up to 98 degrees Celsius. So this equation, it's going to look very similar to our equation for the ice. We still have 250 grams. But now we're using a different specific heat, right? So this is the specific heat of our liquid, not the specific heat of our solid like was used before. And here, we're going to go from 0 degrees to 98 degrees. Again, we're not going all the way from negative 20 to 98. for the water, we're just going to go from the phase boundary up until our final point. Now we have all these temperatures here, and we can add them together. But you're going to notice that the heat required to warm the snow and the heat required to warm the water are in joules. The heat required to melt the snow is in kilojoules. So we need to put these all in the same units, convert them all into kilojoules, and we can add them up, and we can find that it took 196 kilojoules to get this water up, or this snow up to 98 degrees. And nearly half of that energy was just required to melt the snow. It wasn't even the heating part that took a lot. Okay, now let me ask you another question that I think will be very educational and helpful for you in understanding all of this. In the heating curve for water, so right here I have the heating curve. We have the heat added on the x-axis. We have our temperature on our y-axis, and we have our different regions of heating. But in the heating curve for water, the slope of solid only heating, so that's this area between A and B, is noticeably steeper than the slope of the liquid only heating line, that's between C and D. So the question is why? Is it because the delta H of fusion is a lot bigger than the delta H of vaporization? Is it because the delta H of fusion is a lot less than the delta H of vaporization? Is it because the heat capacity of ice is less than the heat capacity of water? Or is it because the heat capacity of ice is greater than the heat capacity of water? Do you want to pause that there and think about that if you can? So the delta H of fusion and the delta H of vaporization don't have anything to do with these slopey parts of the line. Those are these flat areas, right? So this flat area right here is our delta H of fusion. This flat line right here is our delta H of vaporization. So if we're trying to figure out which of these is bigger, whichever one is longer is bigger. So here, our delta H of vaporization is way bigger than our delta H of fusion, right? So this statement right here, delta H of fusion being greater than the delta H of vaporization, is false. The delta H of fusion is significantly lower than the delta H of vaporization, but we don't really care about that part. What we're asking about is this area between A and B and C and D. So a steep slope, what that means is you don't have to add a lot of heat to raise the temperature. If it doesn't take a lot of heat to raise the temperature, that means you have a low heat capacity. So if it takes more heat to raise the temperature, that means you have a higher heat capacity. And so the answer here is that the heat capacity of water is greater than the heat capacity of ice. So you have to put in more heat into water to increase the temperature. Now, this is just a summary of how you're going to calculate different things. If you're heating an object, you're going to use this equation where the heat equals the heat capacity of that object. This is our hard drive example. The heat capacity of the hard drive times the change in temperature. When you're heating n moles of a pure substance, you're going to use this equation. We're going to use the molar heat capacity. If you're heating a mass of a pure substance, you're going to use the specific heat. And if you're melting a solid at its melting point, you'll be using this equation right here, where we're using the delta H of fusion. If you're vaporizing a liquid at its boiling point, you're going to be using this delta H vaporization. So let's just practice this a little more. Let's say we're recycling aluminum cans. The aluminum is heated from room temperature to its melting point at 660 degrees Celsius, and then melted so it can be reshaped. If the heat capacity of fusion for aluminum is 10.79 kilojoules per mole, and the molar heat capacity is 24.2 joules per degree Celsius per mole, how much energy does it take to recycle 1 mole of aluminum cans, which is about 2 soda cans? Okay, now in this part, we have to figure out where we're starting at, right? We're starting at 25 degrees Celsius. We're starting as a solid, so we're heating a solid up until its melting point. And then from the melting point, we are also going to be undergoing fusion. And so, well, I don't know if that's a good example or a good definition, but we're going to be melting it. So we're going to have to figure out how much heat is required for this first part of heating the metal. And then we're going to have to figure out the heat for melting the metal. So our total heat is going to be equal to these two individual heats added together. We're going to have to write out the equations for each of these and plug them in to our equation here. Of course, in the question it says 1 mole of aluminum, which simplifies this a little bit because our N then can be 1. We can drop it. So then our equation just looks like this. We will have to plug in our heat capacity, our specific heat for the aluminum, and our delta H of fusion here. So we're going to put in 0.0242 kilojoules per degree Celsius, multiply that by our change in temperature, and then, where is it? Oops. Put a negative sign here in this equation. That should be a plus. Then we'll add our delta H of fusion, right? So in this case, we're not actually going above the melting temperature, we're just going to the melting temperature, so we don't have to worry about heating any liquid. Do that math, you find there's 26.2 kilojoules of energy required to heat that all the way up and to melt it. Okay. So if we wanted that in calories, which would be a perfectly valid question, so if you want to know how many calories you're going to gain by eating a can of aluminum, you would be gaining 6.26 calories. So the way we find that out is just to take this 26.2 kilojoules, divide by 4.184 kilojoules, you get 6.26 calories. All right, now let's ask this question a little differently. Let's say it takes about 26.2 kilojoules of energy to recycle 1 mole of aluminum. In essence, the aluminum is heated from room temperature to its melting point, then melted so it can be reshaped. If the heat of fusion for aluminum is 10.79 kilojoules per mole, what is the molar heat capacity of aluminum? Okay, so in this, we have the exact same data and information, except now I'm asking you, if I give you this much energy and we get up to this point, what is the heat capacity of the solid aluminum, right? So we're still going through the same process. Our equations here for these different regions are going to still be the same. We're still going to have our molar heat capacity equation and our delta H of fusion equation. We now know that the total energy, though, is 26.2 kilojoules. And so we're going to set that equal to our two different heat regions here. To get the same equation we got last time, again, we're going to recognize the number of moles is 1. But you can see from this right here, right, we could give you a harder problem where we give you 2.37 moles. And that just complicates the math a little bit more. Not a ton more, but a little bit more. Right, so then we solve for our heat capacity here, which is what we're trying to figure out. And for me, I find it easier just to keep the delta T with it for right now. So now we have the total heat minus the delta H of fusion. We're going to just plug these two numbers in. They're both given to us in the problem. We'll find the difference there and then divide by our change in temperature. Then our change in temperature, of course, is going to be 660 degrees minus 25 degrees Celsius. We can work that all out and find that it took 24.2, or sorry, that our heat capacity is 24.2 joules per degree Celsius per mole. If you have any questions about that, let me or a TA know. And then next time, we will talk about how we measure heat capacity in real life. Good luck with your studying. Good luck on exam 2. I hope it goes for you exactly the way you want it to.